my name is Isabella and I will be your host for another mathematics video brought to you by RJ. In the previous video, we derived a closed formula for the floor of the sum of cosines of the harmonics. If you haven't watched them, I suggest watching them now. I left off by asking, can we extend this approximation to higher powers of cosines? Let's take the next simplest step and focus on squares. This brings me to my question for you today. Can we approximate the sum of squares of cosines of the harmonics? First, I'm going to separate this into three terms, two being summations. This is when k equals 1. You'll see why I wrote that separately in a moment. Recall in a previous video that this is the power reduction formula for cosine. Now, let me substitute this into two summations. Let's look at this last term. Since k is even, the 2 reduces to a 1. We already proved in the previous video that the image of each partial sum of cosines of the harmonic lies within a unique integer interval. Adding 1 and dividing by 2 creates a new increasing sequence where the images still lie within a unique integer interval, just like the original sequence. I'll leave it to you to prove that. Therefore, this whole term has an image in a unique odd integer interval, since we found the approximation to be n minus 1. The second term follows the same pattern as the third term. I also leave that to you to check. Therefore, this whole second term has an image in a unique even integer interval, again because of n minus 1. So, we should be done, right? If for both odd and even k the image lies in a unique integer interval, we should be set. Not quite. We still have to consider the square of cosine of 1. This actually plays by a different rule. Why? Because cosines of 1 is negative. We didn't have this case in the previous video. In that video, I explained how the limit of the sums of cosines of the harmonics tend to 0 as n goes to infinity, while the limit of cosines of harmonics tends to 1 as n goes to infinity. This means that the partial sum of cosines of the harmonics mod the integers is always less than or equal to the cosines of the corresponding harmonic. Let's look up both values from the third harmonics for the case of squares. Obviously, 0.995 is not less than or equal to 0.893. After this point, the limit of the sums tend to 0 again. This is where the square of cosines of 1 plays by a different rule. We cannot say that the image of the partial sum of squares of cosines of the harmonics lies within a unique integer interval for all k. Only when k equals 1 and greater than 2. So, what does this mean? Our approximation is a piecewise function. When k equals 1 or 2, approximation is n minus 1. And when k is greater than 2, the approximation is n minus 2. We subtract 1 from the latter part since two images are within the same integer interval. But this is not a closed formula. Can we construct a closed formula? We can construct a closed formula in two ways. One using sign and the other using absolute value. I'll show you both ways. Keep in mind that the functions change when k goes from 2 to 3. And when k equals 3 and beyond, we just need to subtract 1 more. The number 2 has a very special property such that it is the largest natural number that is divisible by all of the natural numbers smaller and equal to it, which means that if we divide 2 by any larger natural number, the result is not an integer. And look here, the function changes right after 2. So, do you know what we use here? I gave you a hint when I said sign. We use the non-integer test function for the divisors of 2. We now have a closed formula for our approximation using the non-integer test function. The other way is using absolute value. Suppose we have a positive number. If we add it to its absolute value, we have twice that number. If we divide twice the number by 2, we have our original number again. If we divide our original number by our original number, we obviously get 1. Now, suppose we have a negative number. If we add it to its absolute value, we have 0. And 0 divided by anything is 0. This is the positive number test function, what I just described. If a is negative, the function computes a 0. If a is positive, then the function computes a 1. Of course, the function is undefined when a equals 0, which is fine since 0 is neither negative nor positive. Now, we need the jump from 0 to 1 to be between 2 and 3. So we need to shift this function horizontally. By how much? We can just pick any number between 2 and 3, not including 2 or 3. Let's just choose the midpoint, which is 5/2. We can do this because n is discrete, meaning n cannot be a number that is not an integer. If we place the positive number test function with a horizontal shift of 5/2 into our approximation, we obtain a closed formula using absolute value. Now, we have two closed formulas for the approximation of sums of squares of cosines of the harmonics, one using sine and the other using absolute value. RJ prefers the version with sine since the original function contains a cosine. Which do you prefer? I'll leave you with one question. Can we extend this approximation to even higher powers of cosines? More specifically, higher even powers of cosines. I hope you enjoyed this video. If you did and would like to see future videos, please like and subscribe. Also, leave a comment telling RJ which areas of math you find interesting. Thank you for watching.